Hello, welcome to Formulaic Utopia. My name is Sarah, and today we are going to be discussing the New York Powerball. That's right, today we're going to be learning how to analyze a data set such as the New York Powerball and also tips for the New York Powerball. So where does the data actually come from that we'll be using today? The data set that I will be using in today's tutorial can be found at data.gov. These come in really nice formats. The one I have is in a CSV, but there are alternative formats also available. If you want to get the fullest and most recent version of this data, you can go through data.gov's source, which is actually data.newyork.gov, to download the full data set or different versions of the data set. All right, so once you decide what data you'd like to use, it's time to load in that data. So we're going to load in the data just from our file path. Then the next thing you're going to want to do is you can take a look at your data. You'll notice that our data looks a little funny. We have a date column that looks really nice. We have a multiplier column, and this is just the winning multiplier for that particular week. And then we have the winning number. So the winning numbers, you can see we have the winning numbers 1, 2, 3, 4, 5 in the Powerball, but they're all in one single cell in each row, and I would rather them be in their own separate columns. So I'm going to just restructure my data set, and we're just going to get our original data back, but now restructured and without the multiplier. Okay, so now that we have our data set restructured, let's go ahead and start to look at the distribution of the data. Let's look at each of the winning numbers and which numbers have won for each of those positions. Okay, so for the first position number, we can see that the numbers that have won have been from 0 to 69, but we can see that there looks to be maybe a little bit of a skew, like low-end numbers have had a tendency to have been selected for a winning number a little bit more often. If we look at winning number 2, we can see that it is skewed, but maybe not as heavily as skewed as winning number 1. It has a little bit more of its distribution is in the center of what numbers it could be, which is 0 to 69. Winning number 3 seems to be maybe the most normal of any of these winning number positions. It seems to have a nice kind of bell-shaped curve to it. You could argue that maybe winning number 4 is kind of the same, kind of normal, maybe kind of the reverse of number 2 here, almost like a mirror image of each other. Maybe a little bit of skew to it. And then winning number 5, it kind of looks like, once again, a mirror image, though, of winning number 1 here. It seems skewed, but skewed in the opposite direction of winning number 1, where it seems like numbers that are kind of larger, you know, between 40 and 69, have kind of had a tendency to be selected more often in the last few years, since 2010 at least. And then finally, if we look at Powerball winning numbers, we can see that that maybe is a little bit skewed, tends to be higher numbers. We also know that there was a change to the Powerball ruling, in which the winning number was no longer from 1 to 39 or 40, somewhere in there, and it changed to 1 to 26, I now believe. So that's definitely part of why there could be a skew there as well. It's important to know. Okay, so now let's go ahead and look at the next plot. Let's look at maybe some box plots. These will also help us look and evaluate the overall distribution. So let's look at each one of those. Okay, so we've got winning number position 1, 2, 3, 4, 5, and winning Powerballs. What we have is the very bottom of the box represents the 25th percentile. The line in the center is your median or your 50th percentile. And your upper box is the 75th percentile of where all of your data is. And then if you see any dots above or below, those are potentially outliers that you're looking at. Those are ones that are significantly further away from the rest of your data. So it looks like we have potential outliers maybe in position number 1, position number 2, position number 4, position number 5. So very interesting, just things to note. All right, so now that we have an idea about the general distributions of each one of these winning numbers and which numbers are often selected each week, let's actually look at the minimum, the median, the max, and the mean and standard deviation of each one of these winning number positions. All right, so looking at this table, what do we see? Okay, so we have that winning position number one has a mean of 11, winning position number two has a mean of 22, winning position number three has a mean of 33, winning position number four has a mean of 44, winning position number five has a mean of 55, and Powerball has a mean of 15. Taking into account that the rules have changed on Powerball from what numbers it can go to and can include. But the rest of these numbers, this is really interesting. What we see here is that on average, winning position one tends to be a lower end number, where winning position number five, in contrast, tends to be a much higher number. So if I was just looking in generally at this and I wanted kind of a fast tip, I might think about, looking even over here at these like box plots. It's almost like a stair step. If I was going to take a guess and buy a Powerball ticket, I might do a stair step where the numbers I choose kind of look something like this mean here. Let's go ahead and look at also whether or not these are normally distributed or not. Right now, we've just kind of taken a guess as to whether or not they're normally distributed, but we don't know for sure. So let's look into that. Okay, so let's go ahead and do a Shapiro-Wilk test of each one of the winning number position columns and just see whether or not that data is actually normally distributed or not. Basically, what this table is showing us is that all of these values would be a value that is less than 0.05, and so that means that the Shapiro-Wilk test is indicating that we should reject normality here. So none of our data columns are normal, even though it looks like potentially winning position number three could have been. We can see that that was, of all of the data columns, the most normal of all of them. It was the closest to 0.05, respectively. Okay, so that's interesting. So the data is not necessarily normally distributed. It just means that since 2010, the way that the drawings have not occurred in a way that has resulted in a normal data distribution. And we can see that through a time series plot as well. In this plot, we have each of the winning numbers, and we can see how it compares to the others. So that's very interesting to see over time as well. And then we have one more plot to look at to evaluate that. What we can see is if we were to overlay kind of those time series plots with each other, ones are kind of down here along with number two. Those are kind of low end numbers where the winning number that gets selected is a low end number, where number three is kind of somewhere in the center. It's those green ones that you see. And then number four and five are kind of the light and the dark blue, and that's near the top of this average winning numbers over months. And then you have the Powerball, which of course is somewhere in between 1 and 26. I wanted to do one final test just to see whether or not the groups are actually different, to test for that as well. We keep seeing kind of a difference between the numbers that get selected in winning position 1 and 2 versus winning position 4 and 5. Those seem to be very different from one another. So could we statistically say that they are different from one another, not just visually? So I'm going to do a non-parametric group difference test using the Kurzweil test. And so from here, I end up getting a p-value that is less than 0.05. And so this is indicating to me that there are significant differences in those groups. I don't know which ones at this point are different, but it is indicating to me that significant differences do exist. Okay, so I'm going to continue onward. Now I'm going to look into basically a Dunn's test, which would be like a Tukey-Kramer test. Now that I know that there are significant differences in the groups, I want to pin down where those differences exist. So I'm going to go ahead and run the Dunn test, which once again is kind of like a Tukey test, but this one is for data that is not normal. So the initial test comes back showing us the group differences. So between winning number one and winning position number two, we can see that there are significant differences between them. This value is less than 0.05, indicating that these two groups are significantly different. If we go to the next one, we can see that group one and group three are significantly different from each other. group 2 and 3 are also significantly different from each other. What we see in this overall matrix here is that every single pairing of groups is statistically different from each other, which is pretty amazing. So that means that each column of data, or each winning number position column, is really doing its own thing, and they're not performing similarly in any of those winning number positions, including in Powerball as well. Thank you so much. I hope to see you all again soon. I hope we get to keep analyzing and finding tips and tricks together.